everyone, and welcome to the first session of today. The first talk is an invited one. It will be given by Guillaume Hoffmann, and the title is Relation and Domain Changing Modal Operator.
Yes, thank you. So I'm going to present work we are doing in Córdoba, Argentina, with Carlos Areces, Raúl Fervari, Mauricio Martel, and with people in France, Hans van Dietzmark, François Schwarzentruber, and Bastien Maubert, people that are now in Nancy and Rennes. Yes. So I'm going to talk about first modal logics from a semantic perspective, okay, which can be quite different from a lot of work that is presented here. Then I will talk about the relation changing operators, and then quite different kind of operators that are called domain changing, and we also call them copy and remove. Okay. So the way we others work with modal logic is a very semantic way. Okay? This is what we are interested in. So for us, the truth of we care about the truth of a formula and how to interpret it. So we follow the Kripke semantic model. Okay, truth of atoms or propositional symbols depend on the current world of evaluation. We have a possible world semantics, so these worlds are connected by relations. So we can say we work with relational semantics. And so the models are Kripke models. So we have worlds, or we can call them points if you want. We have one or more relations on these points, and in every point, the truth of atoms can change. Okay. So, as we see basic modal logic, we see it without committing to a particular application. Modal logic came from a lot of concrete applications of logic to represent reasoning, like deontic logic, temporal logic, logic to represent more recently program software execution. But in our case, we think about satisfiability of formulas on any kind of model. So on the class of every model. So any relation goes, not only equivalence relations, not only transitive relations, some relation, okay? So our diamond is just a quantifier on accessible worlds according to some relation, okay? So in a model, at some point, diamond phi holds if and only if phi holds at some accessible point or world from the current world. And that's it. More formally, these are the models we work with. Basically, they are oriented, directed graph with evaluation, so decorated graphs. And the kind of problems we are interested in are, for instance, satisfiability, model checking, also logical consequence, semantic consequence. No? If some formula implies another formula, but proving it semantically. All these tasks interest us from the point of view of complexity. So we try to look for results of decidability and complexity. And we like when some problem has an easy complexity class. Okay. And why is basic modal logic a pretty logic, an interesting logic? Well, because it is a quite simple language. Okay, so it's propositional logic with one diamond, and that's it. You can talk about the graphs. So it's simple. It's expressive enough to talk about relational models. It also provides a nice internal perspective on graphs. So you don't have a gut view on the model, but you're standing at some point and walking around in the model. So when you evaluate a formula in a model, you move around, okay? You move to accessible points through the relation. And a final remark is that basic modal logic is basically about describing graphs, moving around, exploring, but you're just looking. You're not modifying the model, okay? I mean, the sentences of the logic are about describing what you can see, where you can go, but they are not about telling what happens when you modify the model. Okay, there is no such thing as removing dots or adding dots or removing arrows. Okay, so this is basic modal logic. So we got interested in taking this basic modal logic, and we thought about an operator called swap. And the swap operator is like the regular diamond, but it does something else. So when you take a relation, when you take one step with a swap diamond, you take the relation and you move the arrow around. Okay? So the operator swap modifies the arrow that you just took. And then you continue as before to evaluate the rest of the nested formula. Yes? So this is a diamond version of swap, and the box version is its dual. And we defined swap logic, which is the basic modal logic with this operator. So this is a logic that has the regular diamond and the swap diamond. We wonder how important is this change of adding the swap operator to the basic modal logic. Okay? So a couple of remarks now. So you may wonder why we do this in the first place. First, modal logic, from a semantic perspective, has a long tradition of experimenting with new operators. Okay? For instance, the existential operator, instead of making you move to some accessible point of the model, lets you jump somewhere in the model. Okay? That it teleports you to some other place. You can have the inverse relation that takes the relation at reverse. You can have counting, counting on the number of successors of the formula, success of the current point that satisfies some formula. I mean, and this is graded modal logic. Yeah. So there have been a lot of experiments over time about just adding one operator to the basic modal logic and see what happens. And usually what happens is that we have a more expressive logic, but that still retains nice properties like decidability of the satisfiability problem. Okay? Sometimes we have a complexity jump, but we still have a logic we can work with, we can automatize. So this is one motivation. Keep on experimenting with basic modal logic. Keep on seeing how much resilient it is to change. To what extent it keeps its nice properties. Also, another motivation to study this logic is that there has been a series of works about dynamic modal logics, which involve binders, so hybrid logic with binders, which are basically like first-order constants with quantification. So you can move around in the model and you can name points in the model. What happens with hybrid logic with binders is that these logics are undecidable. Satisfiability is not decidable. So there have been work in order to tame this problem, to make simpler hybrid logic with binders, but they are all undecidable. Okay? So we wanted to study this logic because we thought it was a very simple dynamic logic with some kind of, not really binding, but model modification that looks a little like binding, and we wanted to see if it was decidable, if it had nice properties. Okay? So this is our motivation. Before talking about this logic, I want to talk about the whole family of dynamic relation-changing operators. Because in fact, there have been work on other relation-changing operators. So the one that is at the bottom left, global sabotage, was an operator introduced by Johan van Bentem a few years ago. And there was a study about modal logic and this operator. So in fact, there is previous work. Okay? And so when we saw that this operator has been studied, we wanted to complete the picture. So we started with local swap. Then we saw that they did some work on global sabotage. So we started to okay, local sabotage. Like you could take a relation, you take one step, and you delete the arrow you just took. But you can think also about global swap. Global swap would be changing the direction of some arrow somewhere in the model. Okay? So that's already 4 different logics. And then we thought, okay, it's nice to sabotage, it's nice to delete edges, but what about adding edges to the model? No? So I thought about bridge operator, locally and globally. So in fact, we ended up with 6 modal logics, each one with being the basic modal logic with 1 dynamic operator. And so this work is about studying all of them. Right. Some example, local sabotage. So suppose we stand in this model at the red point. Does it satisfy gamma in sabotage phi? Phi being some formula, no, it doesn't matter. Well, yes, because you can take one edge and delete at the same time this edge. Okay, this is the effect of local sabotage. Okay. Okay. Now, local bridge. What does it mean? It means you are in one point of the model, and then you go to some place where there is no edge, and you build it. Okay. So here you could build an edge to W prime point. Okay. And then the evaluation continues to the point W prime. Okay. So this is an example of the local bridge operator. You can see it as a Spider-Man operator, no? Like you do like this, and you do an edge, and you go to that place, to the destination point, and the edge remains. It's probably the most drawable logic on a piece of paper, because you only add arrows. Okay. So yes. Global sabotage means when you do a diamond global sabotage, you don't move. You stay where you are, but somewhere in the model, some edge gets deleted. So this could happen, for instance. So there's a difference between local and global operators, that the local make you move, but the global leave you at the place where you are. Okay? Yes? So we have these combinations. I mean, we have these 6 versions obtained by combining the action of deleting, adding, or swapping edges and doing it locally or globally. And what did we find with all of these different logics? That the changes are very important. So it's not a little change, okay? Basic modal logic has 3 modal properties, so you can take any formula and satisfy it in a tree model, okay? Which kind of tells you that the logic is not very expressive, okay? It cannot force loops, for instance. While with all of these 6 logics, we don't have the tree modal property, which means we can write short formulas that force models to have a loop somewhere or to have some inaccessible point. I mean, to be a non-tree model. And it's not hard to find them. The easiest one is the bridge one, which don't even have any propositional symbols. Then the sabotage one are maybe a little more complicated, and the swap one are the most complicated, and then you have to use some propositional symbol. So we already have like a hint that we can do much more than basic logic. Model checking, which was polynomial, is now p-space complete. And worse, satisfiability is undecidable for every formula, while it was p-space complete for basic modal logic. So this is the most, hard, the most disappointing result. In fact, when we started with swap logic, local swap logic, at some point we had a tableau calculus, which we thought was correct and terminating. So I thought, okay, nice, the logic is decidable. We have a dynamic modal logic which is decidable and which can do a lot of funky stuff with the models. And 1 week after, we saw that there was a problem with the Tableau procedure. So in fact, we didn't have any guarantee that it was decidable. And 2 weeks after, we found that it was undecidable by using a reduction from a weak version of hybrid logic with binders. And then this undecidability proof we extended it to the 6 remaining, well, to the 5 remaining logics. So no logic is decidable. We do have Tableau methods, which are non-terminating, and translation to first-order logic. Okay. Why can we have translation to first-order logic? We can have it because all these modifications in the model, deleting, adding, and swapping edge, can be expressed by naming the source and the destination of the edges that are modified. Okay. So you use first-order constant to name these points. And then you can, if you translate well the diamond, you can be sure to never take, for instance, a deleted edge. Okay. So we have all of this logic, all of these results which are quite strong. And they are quite similar in general, but the details are different and they are quite ad hoc. So there's no one proof for all of these logics, okay? They look alike, but they are different. So we wanted to generalize a little these relation-changing modal logics. So we defined a framework where you think about any function that takes a relation, an evaluation point, and that gives you a set of relations and evaluation points. Okay? A set of accessible couples made of relation and accessible points. Okay? So this function it's like an extension of the. It's like a generalization of the relation of a model. That when you have a diamond, you go to some accessible point by some relation. Here, what is accessible is not only points, but points and relations. Okay? Because if you think of sabotage, you have the option to sabotage any successor of your current point, any edge that you can take. So each option is a different relation, a different possible relation. So when you generalize this, you can define for any function, for any relation-changing function, the syntax diamond F, which does this. Okay, so all previous operators are part of this framework. Now, what can we do with this framework? Well, some things. We got a general definition of bisimulations for any kind of relation-changing functions. Okay. So bisimulations are relations on models that tell you when your logic cannot see the difference between two models. And in the case of relation-changing operators, those bisimulations are not only relations on the domains of the models, but they are relations on the couples made by the points and the possible relations of each model. So they are more complicated, but for any function, they have the same shape. So we got this general definition of bisimulation. And if you assume that this function is, has an image that has a polynomially bounded cardinality, well, complexity of model checking, when you fix the model or when you fix the formula, is respectively linear and polynomial. Okay, so you can have some complexity results if you assume some restriction of these functions. So this is what we obtain by trying to generalize relation-changing operators. We had failed attempts also, so we did not manage to have a single tableau calculus that would work for any function f, and we don't see it as possible. Yes, and the decidability also is very. I mean, you really have to do a proof by function, a proof for every relation-changing operator. Okay, so we got all of these results. Okay, so some ad hoc and some more general about these operators. So if you want more detail, we can see after how do these proofs look like. Okay. So, okay, all of these operators are very kind of atomic. Like they are very small bricks of what would be model modification. Okay, we wanted to have things very simple, and these operators are very simple. But when you think about applications like dynamic epistemic logic, you also have model modifications But the operations are very, like they take the whole model and they change a lot of things at once. Okay? So we wanted to make like a link between our operators, or something similar to our operators, and dynamic epistemic logic. So this is what this section is about: copy and remove. So there is a way to represent the knowledge of several agents and how it evolves over time using modal logic, called dynamic epistemic logic. And one way of updating knowledge of some agents is to use something called action models. So let's see one example. Okay, this is a dynamic epistemic model where we have two agents, A and B, and each one has its own relation in the model. And A and B do not know whether P is true or not. Okay, so this is why from the evaluation point W we can go to another place where no P holds. Okay, this is how we represent that A and B do not know the value of P. So now say we want to bring some change to this situation. We want to bring a change where the agent A learns that P is true, while the agent B does not know anything new. Okay, so A learns secretly that P is true. Using action models, we can represent this change by this second model. Okay, this is a model where the evaluation point has a reflexive loop of A. So you can see that the relation A does not go to any point where no P holds. So this is to represent that A learns that P holds. Okay? Because this is the only possible world for agent A. Yes, this is its only accessible possible world for A. While B only sees a world where nothing special holds, okay? And in that world, we have a reflexive loop for the relation A and B, which means that B still believes that A does not know the value of P. So these two models are, on the left, the current situation, the current epistemic situation. In the middle, this represents the change, the update. And with this formula here, so we have a box modality that says that which has the model E inside of the box. So this is something quite particular, that inside of the syntax of the logic, you have one model. Okay, E was the name of this model, and E1 is this point. So what this means is that in this model, at the point W, it holds that after that A privately learns that P is true, P holds. And this is the model we obtain by applying this update to the first model. Okay? So the operation on the model is represented by this symbol. And what do we get is a new model where A knows that P is true and B doesn't know about it. So we can see a couple of things about this new model, that it has more points. So the domain has changed. And this new model is obtained by applying a kind of product between these two models. So basically, we take the product of the two models, and we only stay with the relations that are in the update model, in the action model here. So this is why here we have a B relation that goes back from here to here, from here to here, because B is here. Okay. So it's like a combination of adding more points to the model and then removing some relation, some edges of the model. So this kind of rings a bell, no? This kind of reminds us of sabotage logic. Like, okay, we already know sabotage modal logic. We could use this, but there is something missing, that our relation-changing modal logics do not know how to add points to the model. They do not know how to make the product of the domain of the model. So, what did we do to represent action model logic? We defined product updates, model updates, with two operators, copy and remove. So copy is a new operator that we introduced that replicates the original model, keeping all the accessibility relations between different copies. So just copy the model as much as you need, and you link everything you can as before. And remove deletes precise paths of the model. So it's a kind of sabotage, but more precise, as you will see. So the syntax of this copy and remove modal logic would be the basic modal logic with two operators. The remove one, which takes a path argument, and the copy one, which takes a list of propositional symbols and one distinguished propositional symbols. And paths can be the name of a relation, so the name of an agent of the epistemic model. They can be tests, and they can be combination of paths. So with this, you can describe the path that you want. Okay, and currently it's not clear, but I think with the examples. So this is a path, P interrogation A, Q interrogation. It refers to this precise edge. Okay, so P and Q are not nominals like in hybrid logic. They're not constants as in first order logic. They are simply modal formulas. Okay, so doing the operation of removing this path is this transformation to the model. See? Okay. So the operation of copying takes the original model, takes a list of propositional symbols, and copies as many layers, if you want, and each layer satisfies one propositional symbol. But copying is not enough. We have to build all the missing relations. Okay, so we copy the domain, and we also copy the relations. So if you had a successor here, well, this point has to have as many successors as many copy of its successors. Okay? If we had 3 layers, we would have even more arrows, okay, all over the place. And this is simply copy. So our idea was to represent action model updates with these two operators. Okay, so we were not very happy with action model because the logic has semantic information inside of the modalities, inside of the syntax, and well, it was not very pretty. So we wanted to change this. So now when you want to represent a model update with copy and remove, you first have to copy the model with the copy operator. Then you have to delete every edge that takes you to points where this formula P, which is the precondition where the update should apply, does not hold. Okay? So there's a difference between this model and this model. It misses these arrows. It misses all incoming arrows to the points you don't want to keep. So this is the first step to remove the points where the precondition of the update does not hold. And the second step, I mean the third step, the second remove step, is about removing the edges that are not part of the model update. So for instance, from E1 to E2, we don't have any A transition. So what do we do here? We remove all the A transitions from the E1 copies to the E2 copies. Okay, and there are also other transitions we don't have here that are removed there in our version. Okay. So this is one example of representing an action update with copy and remove. You can see one difference here is that we still have a point here. Okay, we have a point which with the original dynamic epistemic logic does not exist anymore. But with our logic, modal logic with copy and remove, we still have it. But there is no problem with this because this point is inaccessible. Okay, it is in the model, but we can never go there. So it's just garbage that is harmless. So with this copy and remove logic, we could show that we had two equivalence preserving translations from action modal logic with Boolean preconditions.